we're talking about series solutions. And in some sense, there's a few basic things. So the main thing is what we talked about 2 times ago, Monday. And what we talked about is, what does it mean to find a series solution? So it's like, okay, we assume that our answer has this form, sum ckx to the k. We just need to figure out what these coefficients c sub k are. And we plugged it into the differential equation. We carefully and gently massage the expressions to sort of smush it all together, get recurrences, and we find the coefficients, and then we get a reasonable answer. That's the basic idea. That's the important thing. Last time we mentioned radius of convergence. And in that sense, what we care about is we want to say, well, we have an answer. How far does it extend? And so there are limitations on it. So today, it's the last idea. In some sense, it's the last idea of the course. And we're going to talk about what we call ordinary points. And so what is an ordinary point? Well, we say that a point is ordinary if, when we look at this differential equation, y double prime plus p of x y prime plus q of x y equals 0, these functions, p of x and q of x, are, there's a fancy word in the book, analytic. Now, if you don't like this word analytic, let me rephrase it in a slightly different way. One way we could phrase it is as smooth. And let's say very smooth. You're like, wow, it's not just smooth, it's very smooth. In other words, we can take derivatives all the way down, all the derivatives we want, and there's no problems. That's what we mean by very smooth. There's, of course, this more technical definition. It says, oh, it has a convergent Taylor series. Okay, but basically think of it as nothing's blowing up. Not just that the function's blowing up, but the function and derivatives, nothing blows up. Okay, so that's what an ordinary point is. Now, why do we like ordinary points? Well, because there's a fact. Now, we don't have the tools to prove this fact, and that doesn't stop us from using it. And it says the following. Well, suppose we have an ordinary point of our ordinary differential equation. And it should be said that not all points are ordinary. So there's this other concept of things which are not ordinary, which are singular. Okay, so what's nice about ordinary points is that if we have ordinary points, then the series solutions make sense. In other words, they're valid. And not only do we have a series solutions, we have 2. And you might say, well, where are we getting the 2 from? It's a second order differential equation. So we should hope for 2 different solutions. And it says 2 linearly independent solutions. Now, generally speaking, there's lots and lots of linearly independent solutions. When we talk about saying there's 2 linearly independent ones, what we usually mean is we have one where y of 0 equals 0, y prime of 0 equals 1. That's sort of our first one. And our second one is y of 0 equals 1, y prime of 0 equals 0. So if you have these 2, all the rest of them are some combination of those. So those are usually our base ones. So if something is saying, hey, find some linearly independent solutions, these are our generic go-to initial values. Okay, so the point is we have some nice series solutions that work. Not all series solutions work. Some series solutions break down. Or you might say, well, you're like, well, wait, what do you mean by it breaks down? We can't find the coefficients? No, you can find the coefficients. It's just that the series doesn't converge. So it's a worthless answer. This says if you're ordinary, at least nearby, you have something to say. Now there's a question, what does it mean to be nearby? In other words, how close can we be and still say that, yes, things are working out fine? So that comes down to convergence, and that's the moreover part. So moreover, the radius of convergence is at least as large as the distance to the nearest singular point. And I say, okay, great. So if we have an ordinary point, we can say, where's my nearest singular point? You can say, look, my solution is valid as long as I'm closer than that singular point is. Now there's a few small caveats here. And I'm just going to focus on the first one, which goes with the star. Singular points can be complex. Now when we talk about complex, we don't mean complicated. Complex means it could involve imaginary things. So things like with eyes involved. Okay, so let's do some quick examples. We have some ordinary differential equations here. And we're going to ask the question, well, is 0 an ordinary point? Okay. So we can go through these in any order. Should we just go top to bottom, or do you want to jump around? Top to bottom. Okay, so we're going to go ahead. Start with the top, probably the hardest one in some sense, but that's okay. Why should that stop us? So if I want to get into the right form, what should I be doing? Divided by x. So here it'd be y double prime plus sine of x over x, y prime, plus xy equals 0. And now we're thinking, okay, we care about x equals 0, and we see an over x showing up. Uh-oh. Uh-oh. Danger. So we might be nervous. So the question, do we have to be nervous here? Sine x over x. Now sine x over x should sound familiar, like we've seen it for several semesters in a row, ever since we started calculus, even maybe before then, if we had a really cool trig teacher. What do we know? What's something about sine x over x that's interesting? What? So the limit as x goes to 0 of sine x over x is 1. Cool fact, really cool fact. That's what helps us take derivatives of sine x over x. In fact, it turns out that sine x over x is actually a lot nicer than you think. Because of that fact that sine x over x goes to 1, we can say something pretty nice. In fact, what we can say, well, think of it as 1 over x times sine of x, but sine of x has a power series. And the power series associated with sine of x, it's the sum from 0 to infinity. Does anyone know that one? It's negative 1 to the k, x to the 2k plus 1. Because the thing about sine is it's a very strange function, a peculiar function, weird. Some people might even say it's odd. So it has the odd exponents. Divide by 2k plus 1 factorial. Now, put the 1 over x inside. What do you see? Not much changes, except our exponent is no longer 2k plus 1. It's now 2k. So, in fact, this has a beautiful Taylor series. We can take derivatives of any order. And this is valid everywhere. Absolutely everywhere. No problems. It's a wonderful function. Now, x, we should mention this function because, that's our q of x. Is that nice? Is x smooth? Yeah. It's very smooth. So, what's our conclusion about 0? Is it ordinary or singular? Yeah. So, this is ordinary. Now, if we ask another question, where's the nearest singular point? What's the answer? There are no singular points. So if there are no singular points, what's the radius of convergence? Yeah, so the radius of convergence is infinity. So that says if you have a solution, and it is theoretically possible to find it, in practice, we're not going to, because you have to do a lot of multiplication, be very patient, make the occasional prayer to Newton to make it all work out. But you could. And you'd see that this series would be have a radius of convergence of infinity. Okay, so that's the first one. The second one. Well, this looks pretty harmless. Y double prime, already in the right form. X, smooth. Y prime, great. Square root of x, y. So the only thing that we might pause is square root of x. Now, x equals 0. Will this be ordinary or singular? And why? Do we have a vote for ordinary? Do you have a reason for being ordinary?
Because they're both still nice. The square root of 0 is 0.
Right, but remember, we want to be very smooth. So it's not just enough that square root of 0 is 0. What else do we want? We want things like derivatives to be nice. Think about the derivative of square root of x. It has a square root of x downstairs. Is that nice? No. See, square root of x starts to break down as soon as you start looking at derivatives. Another way to think about it is if you look at square root of x, say, well, what's that tangent line at x equals 0? And the answer is it's a vertical tangent line. So it's not analytic at 0. So this is singular, which means that we can't use the tools of power series. We're not going to be able to do anything. All right. Next question.
So that would mean that if we tried to solve this equation using power series, we would not be able to do it?
Yes, if we tried to do it with power series, we wouldn't be able to do it. Now, the reason that we would fail is in order to actually make this work with power series, because there's a square root involved here, you'd have to write square root like a polynomial. See, the thing is, in order to use power series, everything has to look like polynomials. And the reason it breaks down is you can't have square root as a polynomial, because when you try to make it into a polynomial, you have to look at things like what happens to your derivative, and things blow up. What happened here is that sin x over x looks like a polynomial. And I'm using polynomial very loosely here, so I'm thinking anything that's a series is a polynomial. All right, so we had an ordinary one. We had a singular one. We come to our last one. So I'm going to make a little side note here. And I came prepared. So the side note is, if you're in a really nice case, also known as the case where we would only ask you a question, like on an exam, for instance, where you have the a of x y double prime plus b of x y prime plus c of x y equals 0, where a, b, and c are polynomials. Those are the only things we're going to ask. We're not going to throw at you some weird, complicated function like sin x over x. Just like, polynomials like 5 or 6x. Those are the kind of polynomials we're thinking about. Maybe if we're in a really excited mood, x squared minus 1. Really simple polynomials. Okay. Well, what happens? If you want to know what's going on, well, what you do is you say, hey, I really want to have it y double prime plus p of x, y prime plus q of x, y. So what you'd really focus on is b of x divided by a of x, c of x divided by a of x. You say, well, the only problems that can happen are if I'm dividing by 0. And so you come to the conclusion, look at what happens to the function a. So if the function a is non-zero, that's an ordinary point. And when you plug in to a, you get 0, that's a singular point. So whenever the coefficients are all polynomials, very easy to make a decision. So now we come to our third point here. X squared plus 2x plus 2, y double prime, plus xy prime, plus x squared y equals 0. All right. So you notice everything's polynomial, polynomial, polynomial. So the key here is this part. X squared plus 2x plus 2 y double prime. So that's our a of x. Now, the question, what happens at 0? We get a of 0 equals 2, so what does that tell us about our point? It's ordinary. An ordinary point. Now, the question we might as well ask is, what can we say about the radius? All right. So if I want to know the radius, I say, well, let's look for singular points. So that would be, take a of x, set it equal to 0. Or when does x squared plus 2x plus 2 equal 0? So how do we do that? Quadratic formula doesn't factor? Okay, sure, we can do that. X equals negative b plus minus square root of b squared minus 4ac, which will be 8 all over 2a. So that's negative 1, negative 2 over 2, plus or minus. 4 minus 8 is negative 4. Square root of negative 4 is 2i. Divided by 2, you get I. So there's our singular points. Now you notice they're complex. That's okay. Sometimes singular points can be complex. In fact, you might say, well, at what point in the class were we allowed to work with complex functions? And the answer is, it's actually been the whole class. We just never said that. We've been doing complex the whole time. So, now, the big question. The radius of convergence is a distance. So, we have to think about what's our distance. From 0, so here's where we're at, 0. If I think about the complex plane, you have a real part and an imaginary part. So you would say move negative 1 in the real, plus 1 in the imaginary, or negative 1 in the real, minus 1 in the imaginary. Those are your two nearest roots. What's the distance? So you moved 1 and 1, so the distance is root 2. So the radius is at least root 2. Probably is root 2 in most cases. There's this little, at least as large. So it says not only will it converge, it'll converge at least within a distance of root 2. Whatever the solution turns out to be. So there we go. So okay, so ordinary, this is more of a technical note. Basically ordinary says, hey, our answer makes sense. That's what we're getting at. And most of the time, we'll use it in this fashion where everything's a polynomial and the leading term is non-zero. All right, so now our problem of the day. Okay, good. Find series solution for x squared minus 1 y double prime minus 6xy prime plus 12y equals 0. All right. Explicitly state the recurrent solution. Give the first few non-zero terms for the two different sets of initial values. And these initial values, by the way, should be familiar. It's like, oh, these are the ones where you have 0, 1 and 1, 0. And compare the radius of convergence with the one given by the fact. When I talk about the fact, that's referring back to this fact about, just how close can we say that we converge. All right. Lot to do here. Well, so let's begin. So where should we start? Sorry, what? Okay, we can talk about that. First off, is 0 an ordinary point? How do you know 0 is an ordinary point? Yeah, see how all these coefficients are nice polynomials? And you look at this term and say, hey, plug in 0, you don't get 0. We're an ordinary point. And where is the closest place where we could get 0? Where does x squared minus 1 equal 0? Plus or minus 1, right? So the radius of convergence from the fact says, well, at least 1. Maybe just 1, but at least 1. But of course, let's find the series, and then we'll say, aha, now we know it's exactly this. Well, we got to find it first. Okay, so that's what the fact says. So given by the fact says, within 1, we're guaranteed the answers would work. And you'll notice that there's a greater than or equal to. We'll come back to that. All right, well, if you see a problem like this, and again, on an exam, this is probably even more complicated than what you should expect. Expect something even simpler than this. But the first few steps should be mechanical. When I say mechanical, it should be almost automatic. Not a lot of thought needs to go into it. Where do we start? Sorry, writing what? Okay, so we need to rewrite in terms of sums, or think of it as series. So I like to say, let's write down what our answer looks like. So our answer, well, will be the sum, 0 to infinity, ck, x to the k. That's what we mean when we say we're looking for a series solutions. It looks like a series. Now, we don't know everything because we don't know the c sub k. That's what we have to work on. But, at least we have, this is the right form. Y prime. Because there's a y prime there, so we should figure out what y prime is. What is that? K, ck, x to k minus 1, y double prime. Because there's y double prime. K minus 1, ck, x to k minus 2. All right. Do we do y triple prime? No, because we stop at y double prime. Okay, so nothing too bad. It's like, all right, we're saying, what does our answer look like? It looks like this sum. And we say, well, okay, what's y prime, y double prime? Now, on a side note, we will come back to this in a few minutes. If we wanted to, what can we do with these starting points? We could change them. This could change to what? 1. And this could change to 1 or 2. So keep in mind, we have the freedom to change. We may or may not do that. Sometimes you may want to wait and decide whether to do that later on. And so let's hold off, and then we'll make decisions in real time, whether we want to make any changes. So now to begin. So up to this point, we're still not having to put too much thought in. The last part without too much thought is just to replace each one of these pieces with what they correspond to. So x squared minus 1, then I say y double prime is the sum. Sum k equals 0 to infinity, k times k minus 1, c sub k, x to the k minus 2. Minus 6x, y prime, write down the sum. The sum, k equals 0 to infinity, k, c sub k, x to the k minus 1, plus 12y. So plus 12, write down the sum for y. Sum, k equals 0 to infinity, c sub k, x to the k. All that equals 0. All right, now comes the time when we start doing a little bit of thought. What are things we need to do? Okay. Distribute, which you can think of as moving things inside. So I can move the 12 inside. That won't be too hard. I can move the 6x inside. Again, no big surprises. Here, the x squared minus 1. Do it individually. So in other words, do the 1 and do the x squared. But do them separately. So you'll actually have 2 pieces from here, a third piece, and a fourth piece. So we're going to have 4 pieces altogether in our next line. So if I multiply by x squared, what does the sum become? Zero to infinity, k minus 1, c sub k, x to the k. Yeah. Well, the thing that happens is I multiply by x squared, which changes the power of x from x to the k minus 2 to x to the k. The minus 1 just means, well, just copy the whole thing and just make sure you have a minus sign. Sum k equals 0 to infinity, k minus 1, c sub k, x to the k minus 2. Okay. When we multiply the 6x through, what does the inside become?
Negative 6.
Okay. All right, there's 6k, c sub k, x to the k. The last part, what happens? 12 c sub k, x to the k. All that equals 0. All right. So again, we recap. We have our form for y, found our derivatives, plugged our derivatives in, and multiplied our little polynomials inside, breaking up the first polynomial a little bit there. All right. But we have a direction. We're not just randomly doing stuff. Where's our direction going? What is it we want to be doing? Combining. We want one sum to rule them all, right? So if I were to combine, what would I need to have happen here? Need the same powers, right? So I have x to the k, I have x to the k, I have x to the k. That's great. Uh-oh. That one's not x to the k. What do we do about that one? Okay, substitution. You can also call it reindexing. So what do we do? What's our new name? L, all right. L equals k minus 2. Okay, so let's do that sum, since that one's going to be the hardest one. So sum k equals, L equals, where do we start? Yeah, well, we'll come back to that. And then what? Oh, I should say infinity will always stay infinity. It's hard to budge infinity. So if L is k minus 2, what is k? L plus 2. And then, what? L plus 1. C, L plus 2, right? If L equals k minus 2, k equals L plus 2. And we have x to the power L. Now, so that's that one sum. Now, the rest of these, we're already happy with them, but just because it'll make it easier for us to read, we're going to also change all the indexes to L, just so everything has L all the way across. So minus the sum, okay, L equals 0 to infinity, 6L c sub L x to the L, plus the sum, L equals 0 to infinity, 12 c sub L x to the L. And of course, we won't forget the first sum. The first sum, L equals 0 to infinity, L minus 1, c sub L, x to the L. All right. And all this equals 0. So this middle sum, or, well, not really middle because there's 4 of them, but this sum had to have some work done. Now all the powers look the same, x to the power L. Now what's our concern? Our starting points, 0, 0, 0, negative 2. Ah, negative 2, what? But wait a second. Remember how we said we have some sort of fudge room we can do here. What happens when you plug negative 2 into this expression? You get 0. What happens when you plug negative 1 into this expression? 0. So where can we really start? So we can start with 0 and not change anything. Because essentially when we pull off those first two terms, at -2 and -1, we're pulling zeros off. So we can just say, okay, well, just start at 0. And now we're like, wow, this is great. Because we have our powers all agree, our starts all agree. So what do? Combine it all into one sum, our one sum that we were after. Okay, so let me, where's a blank piece of paper? Here we go. Nice blank piece of paper here. Move it up. So we have a sum, L equals 0 to infinity of, we're just going to go through term by term, L minus 1, CL, that's the first one, minus L plus 2, L plus 1, CL plus 2, that's the next term, minus 6 L C sub L, and plus 12 C sub L, all that times x to the L equals 0. All right, so that, we took our 4 sums and mushed it all together into one sum. Okay. All right. Good. Well, there's our sum. What's our conclusion? This is a big polynomial. Over here is a really big polynomial. Doesn't look like it, but it's another polynomial where all the coefficients are 0. So the coefficients have to match on both sides, which means that this expression here has to equal 0. And that has to be holding for wherever the sum range is over. So for all L starting at 0, we have that relationship. So when we talk about the recurrence relationship, this is where we're grabbing the recurrence relationship. Now we're going to clean this up a little bit. Okay, so let's see what we have. So when I say we're going to clean it up, we're going to combine, because you'll notice we have several places which have C sub L's in them. So it makes sense that those should all go together, whereas the CL plus 2, well, that'll just be by itself. So let's see. So minus L plus 2 times L plus 1, CL plus 2. So I'm just going to grab that one. And then plus L times L minus 1 minus 6L plus 12 CL. And then that equals 0. Let's clean this up a little bit. This looks like we can rewrite it. What will this become? Some people are really fast. So L squared minus L minus 6L becomes minus 7L plus 12. And someone says, hey, that looks like it factors. Wow, that would be cool if it did. And it does. It's L minus 4 times L minus 3. Okay, now I want to solve, and I want to solve for CL plus 2. And the reason I want to solve for CL plus 2 is I want to solve for essentially a high coefficient in terms of an earlier coefficient. So L plus 2 comes after L. So that's why I want to solve for this coefficient. So moving things around, it's not too hard to move things around here. CL plus 2 will be equal to, well, L minus 4 times L minus 3 divide by L plus 2 times L plus 1 C sub L. And this is perfectly fine And this is a nice, valid recurrence relationship. This is for L greater than or equal to 0. There's something that you could do, and this is something I'm going to do, is I oftentimes like to phrase it here. I don't want to have this as L plus 2. I'd like to just have this be like Cn. So I'm going to do one more sort of re-indexing. So I'm going to call L plus 2 Bn. So C sub n, the L plus 2 down there becomes an n. How about L plus 1? What would that be? N minus 1. L minus 4. Well, if I have L plus 2, how do I get L plus 2 and make that L minus 4? What do I need to subtract from there? I have to subtract 6 from both sides. So N minus 6. L minus 3 becomes N minus 5. C sub L becomes N minus 2. So there's another way to phrase this. And this is going to hold, well, if this started at 0 and n is L plus 2, then this will hold starting at 2. So either one of these is great. And so this is our nice recurrence relationship. Okay, good. Now you might say, why is that good, Steve? Because that was the very first thing it told us to do. Explicitly state the recurrence relation. Done! Check! Okay, so we got that done. Now we have to actually give some non-zero terms for some starting places. So, maybe we can fit it into here. So y of 0 equals 0, y prime is 0 equals 1. We'll start there. And as a reminder, our answer is y equals the sum from 0 to infinity ck x to the k. So when we talk about y of 0 equals 0, in terms of our coefficients, what information are we being given? C0. This y prime is 0 equals 1, what is that telling us? C1. Now, we're going to make a nice little observation here. When I'm looking for a coefficient starting at 2, I always go and say some multiple of the one 2 back. What can we say about C2? C2 is some multiple of C0, but C0 is 0. How about C4? C6? C7? Well, we don't know. That's an odd number. C8, though, we do know is 0. So we do know that C2n will equal 0. Because every time we go 2 back, well, another way to phrase this, if we go 2 forward and we're 0, then it's got to be 0 again. Okay, so the next interesting case is C3. So let's plug in n equals 3. What do we have? C3, according to this rule, is what? Negative 3, because you have 3 minus 6. Negative 2, 3 minus 5, divide by 3 times 2 times C1. Well, what does that simplify to? One. So the negatives cancel. 6 over 6. And then C1 is 1. How about C5? What? You didn't even give me a chance. Well, somebody pointed out, hey, look. You're going to get 5 minus 6 is negative 1 times 0. And of course, it's hard to recover from 0. So once you see that 0, you're 0. Well, what does that say about C7? C9? C11? So all the rest are 0. In fact, that says in this whole infinite sum, how many terms do we have? Just 2 terms. That's it. So not only do we get the series, we get the whole answer. So we have the C1, that's the coefficient of x, and the C3, that's the coefficient of x cubed, and there's our answer. So we have one answer. That's pretty nice. That is pretty nice. Well, but we have a second case. Let's see what happens in that case. In the second case, y of 0 is 1. Y prime of 0 is 0. Well, again, same idea, C0 and C1. When they give you initial conditions, they're really giving you the first couple coefficients. Okay, so we have the first few coefficients. What's going to happen with C3? 0. C5, C7, C... So the odd coefficients are 0. So all the odd coefficients are going to be 0. Okay, so we really just care about the even coefficients. So let's start with C2. So according to the rule, what is C2? -4 times -3, divide that by 2, times 1, C0. So I'm using this relationship with plugging in n equals 2. 2 minus 4, 2 minus 5, 2 times 1, C0. So what does this simplify to? Yeah, because you have 12 over 2 times 1. All right, well, that's interesting. How about C4? Oh, you guys are fast. Let me see. Okay, so what do we have? We have -2 times -1 over 4 times 3 times C2. Well, that's 2 times 6, because C2 is 6 over 12. 12 over 12 is 1. Yes, cool. How about C6? 0. Is it? 0. Oh my gosh, wow, 0. Yeah, it's hard to recover from 0. 0 times 1 over 6 times 5 times your C4, which is 0. So what do we know about after that? So like C8, C10, those things. 0 as well. So once we get 0, every other one from that point on is all 0. So that means, again, almost everything disappears except 3 coefficients this time. So what do we have? We have y equals C0, which is 1, C2, 6, x squared, and C4, 1, x to the 4th. And there's our other solution. That's the complete solution. All right, so now we have these two solutions, and these are, in some sense, they give all the solutions. So any solution to that differential equation is some combination of that. Now, we're almost done. We just have to do a little comparison. The fact that we talked about before says within 1, we're guaranteed to converge. But it's possible that the stars align and that it might extend past that point. But maybe, maybe not. You don't know. How about for us? Did the stars align? What's the radius of convergence of these two series? Yeah, infinite. If your series collapses and it's only finitely many terms, it will always converge because it's just a polynomial. Polynomials converge everywhere. So these converge for all x. And that's our comparison. So there we go. All right. Well, see, it didn't take all of the time. We have 5 minutes left. Should we try another problem or should we call it a day? All right. I feel your enthusiasm. Okay. We'll call it a day. I think that's not a bad idea. All right. We will see you next time.